So this project was to make a low frequency AM transmitter and receiver pair. And here on the screen I'm showing the schematics that I designed myself and then implemented on the breadboard. So on this side here you can see the transmitter. It's broken up into three parts. We have the oscillator, which is a wine bridge oscillator made from a TL0801 CP op amp, tuned to 100 kilohertz approximately. And the second stage would be the mixer. So our input message signal for perhaps an audio signal comes into here. It's mixed with the oscillator signal using an op amp as a mixer in order to isolate them from one another due to the high input impedance of the op amp, of course, and which is then turned into the product of those two signals at the op amp output. And then DC signals are eliminated using a capacitor here. So then over here we have the receiver schematic also, which I designed. Of course, in order to do AM demodulation, on here we have on the left an identical oscillator to that present in the transmitter, and this is mixed with the incoming modulated signal using an identical mixer, which it's also important to note that the signal is referenced to ground using a very high resistance. And this was implemented for practical reasons in the circuit so as to prevent the output of the low-pass filter in the next stage from saturating, essentially keeping the signal strongly referenced to ground, since we're not using a power supply in this project, but simply using 9-volt batteries to power the op amps. And then, of course, but after doing this mixing, due to the Fourier convolution property, we're going to end up with spectra at twice the carrier frequency, plus or minus twice the carrier frequency, even after mixing, even after we've stepped down the signal to zero frequency. So we want to get rid of those high frequency components, of course, using a low pass filter. And this low pass filter is tuned to approximately 1500 hertz, so that operates at very low frequency audio, but very easily gets rid of our high frequency components that result from this mixer stage here.
So here we have a simple AM transmitter and receiver, not using an antenna. It's simply going to idealize transmission by connecting the two with a wire, which you can see here. I'll connect it after, simply to demonstrate the AM principle. So let me just walk through each stage of the circuit here as a demonstration. So first what I will do is measure, connect an oscilloscope to an oscillator over here. So this oscillator is tuned to 100 kilohertz as its carrier frequency. It's a somewhat low carrier frequency, but since we're using op amps here, it's a TL0801 CP op amp from Texas Instruments. We can't get too high with the possible oscillations. So I'm going to connect my oscilloscope here to its output, and let me show the measurement on my computer screen. So you can see here, I haven't yet connected an input signal. I'm just demonstrating the oscillator. Let me change its divisions. So you can see here it's oscillating at 100. If you measure it here, if I stop it in time and you go ahead and measure it here, you'll find that it's approximately 100 kilohertz. Of course, something to notice here is that it's not a perfect sine wave. The edges are clearly somewhat squarish, and this is due to the oscillator not being tuned quite as well as it could be regarding its negative feedback. There are definitely some other oscillatory elements making their way in, and in that sense this oscillator definitely could have benefited from putting a potentiometer in, so that it could be tuned to get it just right regarding the stabilization of oscillations and get this to be a more clean sine wave, but we'll work with it. Okay, So I'm going to stop that. And then next what I'm going to do, I have here an arbitrary waveform generator connected from the same oscilloscope. And so let me change where I'm measuring from. I'm now going to go ahead and turn the waveform generator on. I'm going to use a sine wave 400 Hertz with 2-volt amplitude to simulate just an audio signal. So I'm going to go ahead and turn that on. Let me just show you really quick that that is the signal we're inputting. And you can see here it is the sine wave that we are looking for. I changed the time divisions, that's why I changed the time divisions before I put the camera on the screen. So, and now let's just go ahead. I'm going to put it back on the circuit. This here is a mixer made from just the same op amp with the output of the oscillator severely attenuated so as not to dominate the signal. I used an op amp as a mixer simply because it has a high, very high input impedance, and that means that it's going to be able to effectively isolate the oscillation from, or the oscillator from our input signal so that they don't mesh with each other before actually being output on the wire. It provides good isolation in that sense. And then, of course, since it's going to amplify their differences, they're theoretically different, have differences at every point, so that the output, we should just have the same, or them multiplied by one another on the output. And that's exactly what we're going to see. Of course, I have a capacitor here to get rid of any DC signals, so let me go ahead and connect it. And then here on the screen, you can clearly see, let me change the time divisions a little bit, and the scaling. You can clearly see that this is the same sine wave that we had originally input, except now it's modulated according to that 100 kilohertz carrier, and hence why it's got all these, you can see the oscillations built in there. Let me go ahead and adjust the time division a little bit more. If I stop it in time, you can see that is clearly what has happened. Our input 400 hertz sine wave has been multiplied by the 100 kilohertz carrier wave to produce this AM modulated signal, transmission signal. So now what I'm going to do, in order to idealize transmission to the receiver, I'm going to connect it. But let me first demonstrate that the receiver also has an oscillator. I'm going to connect my oscilloscope to this instead. So here I have it. Let me change the settings on the display. So this one is actually tuned much more cleanly than the other oscillator, simply due to imperfections in the discrete elements used here, since this clearly has a much nicer sine wave. I changed the time division so that if I were to stop this in time and you measured according to these divisions, these are microsecond divisions, I should say. 5 microsecond divisions, that is, so 5 microseconds, 10 microseconds, you'll find that it's 100 kilohertz sine wave. So now what I'll do is I'll connect them in order to idealize their transmission. Remove the oscilloscope. I also have it here, it's being attenuated at this op amp since the input signal, the transmitted signal, is going to be a much lower amplitude than the oscillator over here, and for that reason we just don't want, it'll mix better over here if we attenuate the signal a little bit. And again, we're going to mix it here using another op amp, essentially identical to our mixer over here. And of course, what's going to happen in that case is that since by mixing here, we shifted the frequency from centered at 0 to centered around our carrier frequency, and now over here by mixing it again, we're going, by the convolution property in the Fourier transform, we're going to recopy our signal at the 0 frequency location and also at the double carrier frequency locations, which of course will require us to use a low-pass filter to get rid of those high-frequency elements, and that's exactly what we'll see. So our input is over here. I have the input is going to be referenced to ground with a 200 kilo ohm resistor. I found that what happened was that when I was originally testing this at the output over here, at the output of the low-pass filter, the signal would sort of, it didn't look very clean, and eventually it would almost crawl up the oscilloscope output, that is, until it simply saturated the op amp. And I was able to reset this effect every time I went and measured the transmitted signal again. And I figured out that what was happening is that, like, every time I went to measure the input signal, I was essentially re-referencing it to ground, and that would sort of reset the effect. And so I figured I could achieve the same thing by simply putting a very high impedance resistor between the input and ground to keep it constantly referenced to ground, likely caused by the fact that I'm simply using batteries here. I have no real true ground going on. The ground, so to say, is simply the midpoint between the batteries. And this worked, so let's just go ahead and now